Thanks. Thanks for the introduction. Hello, everyone. Thanks for joining today's presentation. It's about coupled optimization of active and passive components in e-machines towards performance target and also some reliability and EMC targets. Today's agenda, we talk quickly about AVL for those who don't know, and then we would talk about our standard approach for e-machine optimization, usually for performance, cost, and NVH. And then we will talk about the e-machine common mode path or capacitive coupling and how we optimize and include that in GMAG simulation with a use case where we optimize both the efficiency and something like bearing currents, for example. So AVL, we are 11,000 employees worldwide in 45 engineering centers in 26 countries. Since 2013, we have worked in more than 40 SOP series production projects in electrical drive units development and more than 70 sample and small projects and prototype. GMAG was involved in all of them. So our standard approach for e-machine optimization, how we optimize the e-motor, which topologies and so on for cost and performance and NVH, this would present. So basically we start as everyone, you start with the requirements come from vehicle or come from system. You have your simple Excel sheet where you have efficiency target, peak efficiency, cycles efficiency. You have noise targets of the e-machine and also in the e-drive system, and some performance target, torque, power, speed, and so on. And also same for the cost of the material and the cost of the electrical drive. So usually what we do, we start with a baseline or baselines motor and a starting point also in terms of active materials, in terms of a starting, for example, lamination grade, a starting grade of magnets, and the copper. And this we quantify, for example, per active weight of these materials. Then what we do is we define topology or topologies in interest. It can be externally excited motor or one field rotor. It can be axial, induction, PMSM. And each topology we parameterize in terms of macro and micro geometries of the active materials. Also, we include the parameterization of different materials. For example, you can go through different grades of laminations, different grades of magnets, and then with that you can explore every possibility in terms of performance and cost and so on. And with this approach, we have utilized it many times. We have realized an e-drive, for example, lately, an e-drive electrical drive unit in powertrain that we developed that has a WLTC cycle, a driving cycle of 94% efficiency. The full powertrain means e-machine, inverter, transmission, battery. And we have also used such methodology within GMAG that we parameterize everything in one in terms of performance to achieve such challenging WLTC targets and also to have a cost-effective solution, not to overshoot the cost. This is for performance and cost. Similar story also for the NVH or noise. We start with parameterizing topology or different topologies of e-machine. Topologies means, as I said, can be permanent magnet machine, can be any e-machine technology, and also different topologies means in terms of number of slots and poles combinations or all together. And then we quantify the forces, the electromagnetic forces of the stator over the full operation range. And it's not only any forces. So what we do first in GMAG that we characterize what is the NVH orders or what is the electromagnetic critical orders. Not all the orders are equally important. So some, for example, some important orders, for example, in terms of space and time is like the zero space. What we say here, time order and space, time means the frequency of the traveling wave of the electromagnetic over the stator, how fast this traveling. Of course, these orders depend on the topology, means the slots and poles combinations. And the space order, what we call is the shape of the force. Is it, for example, something like that, what we call the zero space order or the breathing mode? This is, for example, is critical when you measure locally on the e-machine housing. You will see this order becoming critical or important. Some other orders with different shapes, like here, for example, the 12 space order that can interact, for example, with the transmission orders, or can interact with the inverter housing. And similar approach after we target these orders and minimize it in GMAG. And then we, here, for example, some measurements we see from A to B sample. You can see on the inverter housing, we reduced up to 20 decibel from A to B sample in measurement. And just by optimizing the electromagnetic excitation forces, same also in the e-machine housing, up to 15 decibel. And with that, we can achieve, for example, the target of NVH, going from a baseline to optimize the electromagnetic forces to achieve the target of the sound power or noise or radiation. Then an example here of global topology selection merged with design of experiment. So first we would start with one topology, parameterize it, create a lot of geometries out of it, something, for example, with 2V, 848 slots, 4 hairpins per slot. And you can see each geometry for a single topology would have a different responses in terms of forces, in terms of losses, in terms of cost. And then we'd add on top of it another topology, something also 2V, 672 slots with 8 hairpins, also with different geometries, will also have a lot of responses, and so on and so forth. We can explore many rotor configuration, many slots and poles combinations with design of experiment, which means the geometry of each topology is also parameterized. And as you can see, then it gets very noisy in terms of the responses, very difficult, or it's becoming very data-driven to manually select what is the optimal topology of optimal geometry. And then here we use optimizer solution. We have AVL Cameo, it's an optimization software. So we get all the responses after parameterization from GMAG, and then we give it to optimization software, where we can create out of these variants a lot of these red cloud variants. Some call it meta model, some call it neural network model. Now there's a trend to call it artificial intelligence model. It's all same. And these models basically can be driven from all of these responses. And from there, we can get Pareto front, or what is our optimal solutions. Can be many solutions. So here we have, for example, optimal topologies with an optimal geometry of each topology. Recent study or project we were doing to find what is the best permanent magnet configuration in terms of cost to the power density and efficiency. So we have optimized with this methodology up to 24 or 26 layouts, different, as I said, different poles, different slots, different number of hairpins. And we then get out of this Pareto front optimal geometry of optimal topology, and we relatively compare them to each other in terms of cost, in terms of power density. And from there we can filter, okay, relatively compare them and filter. Okay, power demand, I can remove some variants. Some topologies would have order collisions with the transmission gears, I can remove. Some would have very high cost, so I can remove. And then we have at the end 1 or 2 or 3 optimal geometries with optimal geometries that we can explore or go further in the project with. Then some of correlation of the quality of this simulation and optimization. We can see here is one EDU where we compared, for example, the simulated efficiency to measured efficiency with average deviation of less than 0.5%. Yeah, we might argue is 0.5% in efficiency too much or too low, but what was important that which local operating points, how it correlates, because it's important, for example, for the cycle. So here we can see the correlation between the cycle efficiency in terms of measurement and simulation. And we can see we had here a front EDU and rear EDU. And we correlated E-machine inverter transmission losses in terms of the cycle with a very good, good correlation. Same for the NVH, also responses we can see between simulation and measurement with a correlation also on the test bed. Then next topic about the capacitive coupling. So all of that was cool. We can develop very high performance E-machine, E-drives, but usually each team E-machine, for example, would focus on its target, electromagnetic target, and then they would send the electromagnetic design to the mechanical team or system team, integrate it, and then cross finger that everything goes well. But can we quantify that? How can we make sure that when you are designing an E-machine early, that it's going to be reliable in the E-axle after integration? Several studies shows that most of the E-machine failures, up to 25%, is happening due to the insulation of the motor. And either locally, that the insulation over time get degraded and then short circuit happen, or indirectly, for example, that the insulation oversized or downsized, that, for example, it can create electrostatic discharges indirectly in the bearing due through the common mode voltage. A true story, we had an OEM last few years came to us after we released the vehicle in the market. The vehicle was 70,000 euro, and it stayed in the road for 80 kilometers, and then it broke down. So very good investment. I will not say which OEM, but yeah, we had to tear down everything, the axle, the EDU, and the issue was in the bearing. So after vehicle integration, the E-machine was with some housing, some more loads, it was creating more, affecting the capacitance of the bearing, and it was discharging. So the bearing was failing much early after 80 kilometers. So we are all, let's say, familiar with simulating or analysis of the E-machine in terms of electromagnetic inductance, saturation, nonlinearity, the resistance, AC resistance. But the E-machine has also a capacitive behavior, what we call parasitic capacitive behavior. This parasitic capacitive, this with equivalent circuit, you would have, for example, from the winding to stator or to the frame, you would have from rotor to stator, you would have also from the winding to rotor, and the bearing itself also has a capacitance. And what is actually affecting this capacitive behavior? So first, the passive components in the E-machine, the insulation system. So anything with permittivity, basically. So the geometry, for example, of the slot liners, the slot paper, the wire enamel or the hairpin coating or the wire coating, so the geometries of it will have effect on this capacitance, and the material itself of the insulation. Here you can see different polymers that is commonly used, the polyamide, the PEEK, and they have also, let's say, the permittivity changes with the frequency and also with temperature. You can see here, it's not really one curve of characteristic in terms of permittivity. And also the E-machine geometries itself would have effect on the capacitance, how the micro geometries, the air gap, the stack length, the rotor diameter, and also all of that interact later than when it was integrated, after the integration with the inverter switching frequency and the DVDT, how fast the inverter switches. So first, let's see how these capacitance are interacting with the inverter switching and the DVDT. So the current trend currently that we are going to higher voltages, 800 volt plus. We are getting even requests now to develop 1200 volt machines. So we are going more and more with the voltage in order to increase the power density and decrease basically the machine size. Same for the inverter, more switching frequencies are being developed through some technology and power modules like silicon carbide, GaN, and so on. It's your same story to reduce the package, reduce the inverter size, and the switching modules also. Of course, those doesn't come for free. There are some issues comes, for example, some more challenging issues in EMC, more challenging in the reliability, issues in the bearing, and so on. So how this interacts actually with the capacitance. So commonly we have here, if you have a star point machine, which is most common, let's say you would have here on this star point, or what we call the common mode point, you would have an interaction of the three phases voltages, which create something called the common mode voltage. This common mode voltage has different levels: 0, 1/3 of the volt, 2/3 the peak. And this voltage basically depends, of course, on the switching pattern of the power modules and the modulation index and so on. But this is commonly, you can see it can go up to the DC link if you have 800 volt, for example. And these common mode voltages actually then interacts through the capacitive coupling of the motor. So the common mode or the start point of the motor would have then the winding to rotor, stator to rotor, and then the bearings as a capacitance, and then we have also the winding to the frame. And this high frequency common mode voltage will be basically coupled through the bearings with this E-machine capacitance, right? And the common mode voltage has also the higher frequency components. So means you would see the tripling, for example, of the switching. You'll see the switching frequency and the tripling of the fundamental and the tripling harmonics also of the switching and the interaction between them. And this high frequency voltages, not only the amplitude, but also the switching of it will interact with this bearing capacitance and the E-machine capacitance also. So basically, the common mode voltage will be mirrored over the shaft or the bearing through mainly the winding to rotor cap and the stator to rotor cap capacitance by this voltage divider. So a simple impedance or voltage divider calculation, you can get that the bearing or this line, the shaft voltage or bearing voltage, would have this ratio or the capacitance of winding to rotor and the summation of all these caps. And this will be basically a partial mirroring voltage from the common mode voltage was coming as we talked before. And this voltage, if you have it here with high frequency, high amplitude, it will create bearing currents. There's many kind of bearing currents. There is a circulating bearing currents, which is basically happening here more at higher speeds, where the gap between, for example, the ball and the race of the bearing increase. So you have a lubrication, it's more insulating. So it takes a capacitive form. And this, you will see that it discharges through this cap. At lower speeds, where the lubrication film, for example, thickness will be less, it will get to an ohmic behavior and once the voltage here is bigger, or when the voltage here is bigger than this breakdown of voltage of the lubrication, it will actually discharge through the bearings with a whatever current depending on the resistance. This resistance also depending on the speed and so on. So as a use case, as we defined or quantified what can we analyze, we can, or we see the dependencies also between the E-machine geometries and this something like a bearing current, we can actually couple these optimizations together. So we have the geometries of the passive component, active geometry of the machine, the permittivity or different insulation materials, and we can add all of that as a parameters into one single optimization with an optimization target to minimize this bearing voltage or minimize the capacitance basically in the winding to rotor. This is the most effective one. So the approach was similar approach to what we do for active components, that we parameterize everything, but we include also the insulation or the passive components, like the slot paper, the hairpin coating, or the wire enamel, and also the material of the insulation itself. And we can create one single design space. Design space means all different combination of geometries, and we can simulate them at the same time in GMAG in two different solvers. Electrical field solver to get the capacitance and then calculate bearing voltages. As you can see here with the electrical field, sorry. And also the electromagnetic solver to get performance, torque, efficiency, and so on. Also to notice that what is the benefit of such optimization is that you can study in an optimizer or something how the winding, for example, winding rotor is a very important capacitance, how it interacts with some geometry parameter or active parameter, electromagnetic. Mostly we call it electromagnetic parameters like the slot open, air gap. But to see that, you see that it's not a fixed value, which means I'm changing something else, like another parameter, the stack length, and you can see the winding rotor, for example, with the air gap, it will change. So this is, we cannot catch manually. This, you need some sort of either design of experiment or optimization to really study where am I in terms of my design and where should I go. And then we check the Pareto front or the optimization target. First study, we remove these capacitance. We said, okay, give me the best E-machine in terms of efficiency in WLTC. So you can see in the y-axis, the full WLTC efficiency, and this is the peak torque. And we get a nice machine with 94.4 only with electromagnetic optimization. And then I checked it in the electrical field solver, how the capacitance actually look if I'm blind in terms of the bearing or the capacitance. And then we can see that a lot of voltage on the shaft happened. The bearing current are relatively big, and there are discharging happening actually. Discharging here, this charge was based on 15 volt, which means every time this line, the shaft voltage or the bearing voltage are more than 15 volt, this voltage you can get from the supplier, for example, then a discharge would happen in the bearing, which means, okay, I developed a very nice machine, but it's not reliable. And you can see here, this is the value, 0.75, for example, nanofarad. This is for the winding rotor. Now we changed the optimization target to, okay, include the capacitance and minimize the bearing voltage ratio and compromise the efficiency. So you can see we dropped with the efficiency to 93.7. And you can see how also the capacitance got reduced from 0.075 to 0.05 nanofarad, which means the shaft voltage went down from 40 volt to 8 volt, no discharging happening, and you can see also the scale of how the circulating bearing currents has reduced. And then we looked for another solution, compromise both, get a little more efficiency, but also be okay in terms of bearing voltages or bearing currents. And we can find another solution that we get, okay, 94.25% with a little bit increase in this capacitance, little bit increase in the bearing voltage and shaft, but still we are safe in terms, for example, no discharges happening. So we compromised basically both, so better efficiency with a bit compromised voltage ratio. So you can see the summary here or the comparison between the three of them. You can see how they actually look between the three variants. So as you expected, V1, which has the highest efficiency but lowest reliability or highest bearing voltage, you can see it tended to minimize, for example, the hairpin enamel, the hairpin coating insulation, and also the slot paper, which makes sense. You get the most copper fill factor. And you can see here the V2, which reduced the efficiency but maximized the reliability or minimized the bearing voltage ratio. It maximized both insulation, and this one was some kind of middle solution. Here you can see also the bearing, let's say zoomed in, the bearing between the three variants, how it goes from V1 to the minimal and then to the middle one, the middle one. So in summary, the standard approach that we all know, focus only on the electromagnetic, can lead that you don't know what's happening in terms of bearing, in terms of capacitance, or you can be based on experience, usually just size the insulation based on the supplier experience and your experience or from previous projects and so on. It does not mean that it's the best solution or the most reliable. So the coupled optimization, including passive insulation system, including electrical system, high frequency analysis with electromagnetic design can save a lot of issues. So because basically you want to move any issues that will happen in the SOP or in the start of production later where the cost of changes are huge. And also the allowed design changes can be you are not allowed to change anymore. You want to move all the possibility or all the issues to early development phase. And this is done basically with simulation or such all-in-one optimization. So thanks a lot, and I'm ready for the questions.
Okay, thank you, Mohamed. Any question? Yes.
Thank you very much for the presentation. When you showed mainly this electrostatic calculation or the high frequency network calculation, is there a 3D basis used for all these capacitances?
Correct. So the electrical field analysis is done in 3D. Yes.
Thank you.
Hi, thanks for the presentation. I have one question. The question is based on even for adjusting the parasitic capacitance in bearings, the same time it's also affecting the thermal behavior in between the coils and the thermal network. So what would be the best trade-off in between these two?
Correct. So the more, of course, insulation you will add, the less thermal conductivity you will get between the copper and if you have, for example, housing with water jacket outside or even some oil channels here, of course, the thermal conductivity will reduce. But here the study was focused on electromagnetic and this electrical field or capacitance. Of course, you can add on top of that something like what the colleagues before GMA colleagues presented. You can add also the thermal network, and then you would have basically, as I mentioned, the all-in-one. So as I mentioned before, you can add also NVH, you can add the thermal simulation, you can add the electrical field capacitance and so on. So there is no, of course, definite answer. It depends on the design, depends on the everything. But as a showcase here, of course, you can add also, for example, a thermal network, and then you study the thermal conductivity between the copper and the stator, for example.
Regarding the insulation, you can see like when you really simulate or the optimize, like you optimize the insulation thickness quite from small to quite big. And that will affect, of course, this parasitic capacitance and like this bearing current. But what will happen, the breakdown voltage for the insulation. For instance, when you move to like 800 volt, like there is like, certain thickness you really need with the certain, so do you want to make any comment there?
Yes, so some simulation we were doing, for example, in the insulation in terms of checking partial discharges. For example, using also same methodology. Unfortunately, we could not quantify a limit for the partial discharge within GMAG, let's say, because at the end you do something like end-of-line tests at the end of when you have a stator, after the integration of everything, you do end-of-line tests, including, for example, high potential voltage test or surge test or turn-to-turn test. And then you measure, for example, something like the leakage current. I have been in contact, maybe here I open the ticket again for forces, that the electrical field analysis to have a transient or time domain. So currently it's a frequency dependence, but we have been trying to replicate some end-of-line insulation tests with such methodology to check, as you mentioned, the breakdown voltage, to check partial discharge and so on. But most of these tests have time dependency. For example, you stress the insulation for 1 minute, I don't know, it's 50 hertz, etc., or whatever. And we propose that maybe that the electrical field solver can have time domain or transient solution. But yeah, Dr. Yamada's here.
One last question, yes?
Thank you again for this presentation. So the objective function is to minimize the bearing current. That's correct.
The BVR, the bearing voltage ratio.
Is there like you minimize over some representative points in the operating area, or is just one worst case scenario? What is the, let's say, background regarding this minimization of this voltage? So you consider one point, or is over the driving cycle or the complete operating area?
Here it's over the full driving cycle. The operating point, let's say, from what we saw, would affect mainly the bearings capacitance. But for example, the winding rotor, winding stator rotor, it's geometry and insulation based. So the operating point does not play much. When it plays in the bearing capacitance. In this study, we had it fixed, the bearing capacitance, because it's not also very easy to get these data. Usually how the capacitance changing, it needs a lot of intensive measurement and supplier discussions and so on. But here the electromagnetic was focused on the full driving cycle. So this is in terms of the full electromagnetic, and the capacitance was basically out of geometries and out of insulation geometries or the active material geometries.
But this voltage shaft is calculated at which point, or is?
Yes, correct. So here at the end, okay, so you need, I mean, probably this one. Yes, this was peak value. So we had the full 800 volt.
Okay, but the partial load, full load, for example, very low torque, or
at the end it's a methodology use case. You can have, of course, you can cover the full operation range as we discussed. You can basically, you can go through really every scenarios, acceleration scenarios, partial loads, continuous, and so on. Here we used for this study, let's say for the V shaft and the bearing and so on, the full acceleration in basically in the constant torque region on the knee point, basically where everything is maximized, especially the voltage also.
Okay, thank you.
Hello, thank you for your presentation. Maybe I don't understand properly, but I do a question just to understand the point. I mean, the capacitance depend on the insulation layer, isn't it? So why do you do a so complicated optimization to?
No, it was not only the insulation. Actually, you can see, for example, here, it has a huge dependency on some active geometries, like the air gap, for example. Okay. The bigger air gap you have, the smaller caps to the winding rotor. The slot opening, for example, would have also big effect. This, for example, we thought about if you have a wave winding, you know, the continuous wave winding where you insert the hairpin radially. This needs, for example, a big slot opening. And bigger slot opening means you can have bigger capacitance, because when you have a smaller slot open, it can act some sort of like a Faraday cage between the winding, for example, and the rotor. So it can reduce the cap. So as you can see here, it's not only the insulation, of course, the air gap, the stack length, all of that had, I don't know if I play it here, you can see I'm changing the hairpin height, and the whole capacitance changing with air gap and slot opening. So for sure, the geometries also have influence, the active geometry.
Thank you very much.
Question from my side. You're dealing much with capacitive current for the bearing current. Since I see it's quite high frequency, I'm wondering, there is also serious inductance in the distribution path of the bearing current, and this is heavily affected by skin effect, since the frequency is high and we have ferromagnetic parts, especially in the rotor. So I would expect the skin depth is less than, I don't know, 100 microns or something, which will mean you have a very big serious inductance in the distribution path, which I do not see in your schematic. And I could imagine that there is a big effect, especially on the high frequency area, that the bearing current is maybe a lot lower due to this effect?
Yes, there is what we call the asymmetric flux linkage that can happen through the housing. It happens through the bearings, happens through the shaft. This is basically, yeah, sort of leakage flux, actually, which induce inductance bearing currents. Here it was not included in this study. So the inductance, for example, of the system, or how if you have here inductance from the windings, for example, or a flux linkage from the winding to this point, let's also to be honest, in reality, in the vehicle, this point is not a pure zero. In reality, in the vehicle, this would have some resistance and inductance, and this would interlink also and include, for example, an inductance or inductive currents. For example, the vehicle ground system would have influence. So here, yes, this is true. In this simulation, it was not, or let's say it was eliminated from this showcase. But in reality, what you mentioned here, which is the common mode inductance and the common mode resistance, for example, or the grounding impedance would have influence. For example, what we call the frame, in reality, it's not just a zero, absolute zero. There is some impedance, and then you have really the earth of the vehicle, for example, or the ground of the vehicle.
Yeah, thank you. Very nice presentation and very interesting study. I see you're paying a penalty of about 0.5% unit or something in efficiency to solve this problem. Then I wonder, how about?
Yeah, from here, yeah.
Yeah, from
point two, yeah. This to this would be.
Okay, 0.2% unit something. That could be a lot of energy in the lifetime of a vehicle, say commercial vehicle. How about solving the problem with slip ring for grounding?
Yes, at the end, the example of the OEM that mentioned, we had to use the shaft grounding conductive ring. And at the end, we were in literally here, in the SOP. And to change that, the vehicle was already in the market. To change that, you can imagine how much it costed them to change the full E-axle to add the grounding ring of the shaft. There is also other solution, like the conductive bearing, metal bearing, which basically most of the solutions actually create a less impedance in parallel with the cap. So any current or any shaft voltage can basically get released in a parallel, for example, in a conductive shaft ground ring, in a conductive bearings. There are some solution conductive bearing. Tesla, for example, has a patent to use an auxiliary bearing, third bearing, that basically used or put there just to get all these discharges and currents in parallel. All the solutions basically use something very small, parallel resistance, either, as you mentioned, the ground shaft, auxiliary bearings that is short-circuited. There are also some solutions to have an inner shaft inside the shaft, which is also a parallel small resistance that anything can take basically this current that doesn't go here, but it goes through to this whatever auxiliary system. But it comes with cost.
Okay, thank you. So
Thanks.
I would propose to stop here for the question, but there is a break. So if you want to
let's-
continue to ask question to Mohamed, go ahead. So thank you, Mohamed.
Thanks.
So we have a 15-minute break. Please try to go back at around 4 p.m.